Shall we get started?
Yeah, I think we can. Right on time.
Great. Well, yeah, good morning again, everyone. It's a pleasure and an honor to be here as always. So thank you for your presence and attention. So I'm going to be talking today about counterexamples, which are an important notion in mathematics, but also I think can be made into interesting activities for the classroom or for math circles. I think yeah, we'll explore different ways in which we can use this concept to teach and to learn. Um, I based these materials from a link that I got from Dave, but if I'm going to be asking, so I can share this later, of course, but I'm also be asking for input for concrete ideas for how to implement this in in the classroom. Um, so do interrupt me at any time. You can, I'll try to have the chat open, but if I miss the chat, then let me know, and also feel free to just interrupt me and start talking at any moment. If you're muted, which is probably good, if there's background noise, remember to unmute yourself, because otherwise, yeah, I won't know that you're talking. And yeah, if I miss something on the chat, then maybe y'all can someone can let me know. Okay, so counterexamples. So what's a counterexample? So if someone makes a statement that's of the form "all flowers are red," okay, that's a statement that's false. Not all flowers are red. So how would you disprove a false statement such as "all flowers are red"? Well, it suffices to show a single flower that isn't red, like a daisy, and then that's it. The statement is false. So they're relatively easy statements to prove that they're false because you just need to come up with a single example. In mathematics, sometimes showing that something is if you're trying to prove that I don't know all numbers satisfy some property, or you're trying to prove something very general, it might be tricky. It might require some argument. It might require some logical steps. You might have to write it down carefully. This can be quite subtle, even for advanced students in higher education. And yeah, there's a whole art to it. But showing that a statement like "all flowers are red" is false requires thinking. It definitely can. You need to exercise the brain, and it can require creative thought. But it doesn't require much by the way of technical logic or manipulating of symbols or whatever. You just need to show an example. Um, so another thing that I will say is that I think the format in which this activity is phrased is probably going to be amusing for students because students love to dis challenge figures of authority. They love challenging their parents. They love challenging their teachers. So if you phrase there are, often you can phrase a question in different ways, but if you phrase a question in the form, "I'm making this claim, prove me wrong," and then it's up to the students to prove you wrong by coming up with a counterexample to some claim that you might have made, and that can be quite stimulating for them, and maybe is more engaging than if you phrase it in a different way. So again, the statement "all flowers are red, prove me wrong" is maybe more exciting for a student to engage in than if you phrase it in the form, "Okay, I want people to come up with flowers that aren't red," or some other equivalent phrasing that might just be less stimulating or fun. So that's kind of the idea. Um, I had some other things I wanted to mention. So first of all, these materials, like I said, are based on a link that I got from Dave, and I have the website here, mathforlove.com/lesson/counterexamples, and you can have a look at that, and there's plenty of other good materials there. So yeah, another thing that I wanted to say about the counterexamples is having good logical reasoning is important well outside of mathematics, as I'm sure we're all aware. So when students will engage with politics, with the news, when they need to go and do their business, then often having the skill of being able to come up with counterexamples to bogus claims is an important skill. If a politician is telling you, oh, everything is like this, then having the brain agility to be able to come up with counterexamples and be like, oh no, this person is actually not being truthful, because I can immediately come up with counterexamples to that claim that they made, or same in business. So these are, I think, skills that are useful. I think another fun thing about this game or activity is it can be played at several levels. So yeah, so you can play counterexamples with kids as young as kindergartners. It's phrased as a kind of reverse I Spy. So for example, you can say in the classroom, I claim there are no squares in this classroom. Okay, who can find a counterexample? And then the kids will look at the classroom, and I don't know, maybe there's a table that has the shape of a square, or maybe they can see different squares, and there's no single right answer, right? Like any square that anyone can find will be an adequate answer. Um, and Yeah, so then you can transition to more substantial math concepts, okay, and you can use this as a tool to address common misconceptions. So, for example, you can make a claim saying, "Oh, if you double a number, then it's always larger," and then challenge your students to find a counterexample, and they might be stimulated by this, and they might try for a while and not be able to find a number that when it's doubled isn't larger, but eventually someone might realize that if you double zero, you still get zero, or if you double a negative number, then according to our conventions, that's actually not larger, that's smaller. So uh, another example is sorting out why every square is a rectangle, but not every rectangle is a square, right? So you can make the claim that okay, every rectangle is a square. Who can find a counterexample, and someone can point maybe at the window and say, look, that is a rectangle, but it's not a square. So having concrete ways to disprove statements. You see, by the way, in the statement, every square is a rectangle, not every rectangle is a square. So these are two very different kind of statements, right? So the statement every rectangle is a square is false, and the way to see that not every rectangle is a square, well, you just need to look at a single rectangle that doesn't have all sides the same length, and that's it. It's not a square. But to the statement every square is a rectangle, that's a true statement. And to establish that statement, it's not enough to come up with a single example of a square and say that's a rectangle. You actually need to make some reasoning as to why every square is a rectangle. That does involve some slightly more complex logic. It's not too bad, right? You need to put the definition of a rectangle, some polygon with four sides and two pairs of parallel sides and maybe right angles. And then you can have the definition of a square, and then you need to show that everything that satisfies the definition of the square will also satisfy the definition of the rectangle. But you can see that that's already quite subtle if you really want to write it out or explain it in detail, which is why counterexample type questions are more accessible. And then finally, just to mention that, of course, these are relatively simple examples, but if you want to, you can take this at all levels, and you can get to very, very advanced questions. For example, every point on the number line is a rational number. Okay, so that's false. Not every number on the number line is a rational number. Remember, rational numbers are numbers that can be written as the quotient of two integers. But to actually produce a counterexample, it can be a bit tricky. So maybe I can ask, does anyone know any counterexample to the statement that every point on the number line is a rational number? Do we know any number that can be written as a fraction of two integers? You can either write on the chat or just talk out loud. Any suggestions for a number that can be written as a over b with a and b integers? Okay, so you can think about that one, and we can return to this one towards the end. Okay, so I think that's an interesting one, but like I said, quite advanced. So let's get back from the clouds a bit. So what's the specific format? Let's just kind of be very clear about it. So the leader, it can be the teacher, but you can engage this activity through a student, makes a false statement, okay, that can be proven false with a counterexample. And then the group, the classroom, whatever, tries to think of a counterexample that proves it false. And there can be several counterexamples that we can come up with, and in general be good for the classroom to come up with several. So the best statements usually have the form, all flowers are red. Okay, but now let's forget about flowers in red, and just the form of the sentence is all are. Okay, and the first is some class of objects, and the second is a property. Or you can frame it as, no flowers are red. It's different formulation, different question. And then to disprove that, you need to exhibit a counterexample. But in this case, it would be a flower that is red, like a rose. And you can also play with variations of this form, like if it has legs, then it can walk, for example. If it has some property, then it has some other property. Statements like that you can engage them with. Okay, so now I want to go through some examples, but any questions at this point, or comments, or remarks? Okay, so I see something in the chat that it is false that every point on the number line is a rational number. It's true. It's a false statement. But and so to prove it false, we need a single example of a number that is not a rational number. Okay, so if you know of one, or you can think of one, you can write it in the chat. If not, we'll return to this later on. Square root of 10. Okay, I agree that's not a rational number. So now the question is, how do you know it's not a rational number? So again, feel free to comment or think about it, and we can discuss. But yeah, that's absolutely right. So square root of 10 is not a rational number. Any questions about, the general format of the activity, or about the meaning of any of the words that I used, or any other thoughts that anyone wants to share at this point?
Hello, can you hear me?
Hi, yeah, I can hear you.
So it would be like something like all integers are fractions.
Yeah, that's a great that's an interesting one.
Or not fractions. Not fractions.
Right. I mean, I guess it depends what you count as a fraction, right? If I'm allowed to write a fraction with denominator one, then I guess any integer, I can express it as a fraction with that integer over one. Um, so I guess if you phrase it in that way, then it would be a true statement. Um, but you can make it a false statement if you change a little bit the meaning of fraction, um, or if you phrase phrase it in a slightly different way. Okay, but so thank you. So is the structure of the game clear? And we'll have time to make more suggestions for what could be good questions in a second. But I just want to make sure that we all understand the basic structure of the activity. Is everyone happy? Any questions?
None so far, sir.
Okay. So let's have some sample questions. So suppose I make the claim all birds can fly. Okay. Can someone prove me wrong? Is it true that all birds can fly?
False.
Okay. I'm seeing in the chat ostriches. Someone said something, but I couldn't quite hear it. You can speak again, or
Not all birds can fly, sir.
yeah, no, that's right. And how do we know that it's false? Because I can give counterexamples, and
Yes,
we've had.
penguins.
Yeah, that's right. Thank you. So yeah, I'm seeing in the chat penguins, chicken, ostriches, um, and these are all great examples. So all birds can fly. So this is false, but you see, it's not. The point is not to say whether it's true or false. The point is to actually prove that it's false by giving examples, and we have a bunch of them. So penguins, chickens. So these are concrete examples that we come up with, and they show that the statement is false. Okay, so what about the statement, no books have pictures in them? I claim that no books have pictures in them. Is it true, or is it false? And if it's false, I need a counterexample. Okay, I claim that no books have pictures in them. So can you prove me wrong?
False, sir.
Yeah. Okay, so I'm getting all kinds of great counter examples. So Dr. Seuss, more generally children's books, instruction manuals, all kinds of graphic comic books. Okay, art books, maps, all kinds of books, right? And so you already see that you can make this kind of question, and you're going to get all kinds of different counter examples from the group, which is great, because that means that, you know, it's not the type of question where like someone gets the answer and then no one else can participate because that's it, someone said the answer. In this case, there's a lot of different counterexamples that can be given, and so it's a great way of engaging a lot of people in the group. Let's see a similar question, but different. What if I say all books have pictures in them? Okay, I claim that all books have pictures in them. Can anyone prove me wrong? If it's false, then there has to be a counterexample. Or is it true that all books have pictures in them? Yeah, so by and large, adult novels, at least many of them, will not have pictures. Okay, so some of them might have an illustration in at some point, but for the most part, adult novels don't have pictures in them. And you see that it's kind of interesting that both the statements "no books have pictures in them" and "all books have pictures in them," both of those statements are false. And the counter example, yeah, Braille books, totally, government publications, yeah. Well, all books have pictures on the front cover. I don't know. I've definitely seen some books without pictures on the front cover. Sometimes you just have the title of the book on the front cover, maybe with some color on the front. I agree. A lot of covers will have pictures, but definitely not all of them. Here, if I wanted to be really pedantic, I would actually need a specific adult novel, right? So actually, we should get a. So we should find a specific one that doesn't even have pictures on the cover, because as the comments are pointing out, then some adult novels do have pictures in them, at the very least on the cover. And so saying adult novels doesn't quite cut it. I'd have to find one specific example of a book, but maybe then that could be like a game for students in the classroom to go and try to find a specific book, or if it's not this, it could be a similar question, right? But it could then become a game to find some object in the classroom that you can use as a specific counterexample. Oh, it looks like Dave has a specific counterexample. I think you're muted, Dave.
Yeah, it's kind of fun, right? You're wrong. You lie.
Yeah, I'm very untrustworthy. So let's keep making false statements. Okay, I claim that if something produces light, then it is a light bulb. Is it true, or can someone prove me wrong? Okay, fireflies. I'll say it again. I was saying if something produces light, then it is a light bulb. And I'm getting fireflies, the sun, plenty of counterexamples. The moon is going to be a tricky one because it reflects light from the sun. So does it produce light? I guess maybe it depends on how you interpret the word produce. But I think the stars and the sun definitely produce it. Fireflies, I think, definitely produce it. Lightning is a good one, and you see even I think one also great candles, fire. One great aspect of this game is that even when the answers are you might disagree with some of the answers or not, but then you have a chance of discussing why you disagree with some of the counterexamples, if indeed you do, and the conversation of why you disagree with a proposed counterexample can lead to some interesting discussion into some thought-provoking conversations. Okay. What about if something has stripes, then it is a zebra? Is that a true statement, or can someone prove me wrong? Okay, I'm hearing false, but I want counterexamples. Okay, great. So I've got tigers, bees. Okay, so you see, someone telling me false in the chat, I'm like, well, you're wrong. Like that's or that's just your opinion, you know. But if someone is like tiger, then that's it. I've lost. The statement is just clearly false because someone has produced a counterexample. So just as a rhetorical tool, actually giving a concrete counterexample is Nemo. That's right, like clownfish. Someone giving a counterexample is such a more powerful way of countering an argument than just saying you're wrong or you're false. There's really nothing I can say if I make the claim that if something has stripes, it is a zebra, and then just someone points out that a tiger has stripes, but it's not a zebra. Like that's the end of the conversation. Yeah, clothes is stripy clothes is an interesting example because I guess we tend to think of counterexamples that are as similar to the proposed object as possible. Like you were saying zebra, and so we can think tiger, hyena, because those are animals that have stripes. But really, the question was a lot more general: is if something has stripes. So yeah, you have a stripy pair of pants. That's a perfect counterexample. It's something that has stripes and is not a zebra. Yeah, rainbow. We could indeed think of a rainbow as having stripes. Whether the colors of the rainbow change continuously, or whether we've decided culturally to separate it into a bunch of strips, could also be an interesting follow-up to that proposed counterexample. So you see, you can talk about what are stripes, how do we know a stripe, Navajo rugs. Yeah, so that's all great examples. So let's have a look at this one, which again goes a little bit in the direction I was mentioning. So everything that has legs can walk. What do you think about that one? Is that a true statement, or can someone prove me wrong?
Balls, tables have legs.
Okay, great. So you see, tables have legs, but they cannot walk. Chairs have legs, but they cannot walk. Indeed, someone that's disabled, so some disabled people might have legs but cannot walk, but or injury. So injury, disability. So these are all examples. I think the counterexamples of tables and chairs are quite interesting because again, if you think everything that has legs, maybe the most natural thing that someone would think about is like, okay, an animal. So let's try to think of animals that have legs but cannot walk. But you really need to take the statement as it comes. The statement is everything that has legs can walk. And so you in order to disprove it, you just need to exhibit a thing that has legs. It just means that in our common language, we refer to it as having legs, but cannot walk. And tables and chairs are perfect examples of that. Okay, let's think of a slightly harder one. I claim that no square has a perimeter equal to its area. Okay, let's agree on some unit. I don't know, centimeters, for example, or inches. I don't care. And I'm going to claim that no square has a perimeter that is equal to its area. Either the statement is true or the statement is false. And if the statement is false, then in order to prove me wrong, you just need to show me a single square for which the perimeter is equal to the area. Okay, but I claim that no square has perimeter equal to its area. So let's see if someone can prove me wrong. Maybe it's true. Maybe no square has perimeter equal to its area. One inch? Well, a square that's 1 inch by 1 inch is going to have perimeter 1 plus 1 plus 1 plus 1 because it has 4 sides, each of them 1 inch long. And so that's 4 inches total perimeter. But the area would be 1 by 1 equals 1 square inch. So in that case, the square and the perimeter and the area are different. So
the areas, sir,
yeah,
it is false because an area is the space occupied by a polygon, while the perimeter is the distance around a polygon. So there is no possibility that an area and a square of a square is equal.
okay, fair enough. I love this answer, and I'm inclined to agree with you that we shouldn't really be comparing perimeters to area, because perimeters are indeed measures of length, whereas areas are measures of length squared. And so it doesn't really make sense to compare them. So maybe I should refine my question a little bit. No square has a perimeter whose magnitude is equal to the magnitude of its area. Okay, so by this I will mean the perimeter will be a certain number. Let's say inches. Let's work in inches. The perimeter will be a certain number of inches, and the area will be a certain number of inches squared. And what I'm asking is there a square for which those two numbers are equal? Okay, and I think we have the counterexample has been posted in the chat. So if you have a square that is 4 inches long, then the perimeter is going to be 4 plus 4 plus 4 plus 4, which is 16 inches. And the area is going to be the 4 by 4, because it's the square of the side length for a square, and that's 6 inches squared. Okay, so I completely agree with that comment that we shouldn't really be comparing things that are in different units. That's kind of a general philosophy of life. We shouldn't be comparing things that don't have the same units. But I modified my question to be a bit more precise. This, by the way, is a great dynamic to have in the classroom too. Like a student might object to the phrasing of a question, and then you might think about it, and if you agree, you can modify the phrasing. And this is all kind of a great way to think about these questions. So anyway, with the modified question about just whether the magnitudes of the perimeter and the area can be the same, then we have a counterexample, and that's it. The counterexample is in whatever units you have, a square that has 4 units as side length, because then the perimeter will be 16 of those units, and the area will be 16 of those units squared. Is that clear to everyone? Are there any questions about this one? This one kind of was a little bit more subtle.
None so far, sir. It's clear already.
Okay. Anyone else have any questions? So you see, I think the kind of formulation of the activity is fun. You know, you tell the students, no square has a perimeter whose let's just do the simpler version. No square has a perimeter that's equal to its area. And then they might be like, oh, I'm gonna prove that teacher wrong. And then they might like start thinking and stuff. Whereas if you tell the students, okay, everyone, I want you to find a square that has the same perimeter as the area. It's a little bit less exciting just because you're not proving the teacher wrong. you're not challenging the authority. So I think just that slight turn of phrase can make many questions just a little bit more spicy, and therefore can help a little bit with engagement. Okay, let's maybe do a couple more. So let's do this one. Multiply two numbers, and you end with a product that's greater than both the numbers you started with. Is that true? If it's false, I need a counterexample. Is it true that if I multiply two numbers, you always end up with a product greater than both of the numbers that you started with? Okay, so we're having a bunch of great counterexamples, so it's false. So first of all, if I multiply any number by 0, I get 0. Another counterexample was multiplying 1 by 1. Then I get 1, which is not greater than 1. It's the same. But again, one nice thing about this type of activity is that there's many, often there's many different counterexamples that you can give. So what's a different kind of counterexample to this problem? So we've seen kind of two types, one of which is when one of the numbers is 0. I think another kind of special counterexample is this 1 by 1 equals 1. There's kind of another interesting way in which I can multiply two numbers and end up with a number that isn't greater than both of the numbers I started with. Can anyone think of any other counterexamples? Kind of different. Fractions. Okay, that's great. So I can multiply, I don't know, 2 by a half, and I get 1, which is and indeed I can negative. So if I multiply -2 by 3, I get -6, which is smaller than 3. So you see, this statement can be false in kind of several different ways, and it's fun. Even when someone has always given a correct answer, you can keep fishing for other counterexamples, maybe different ones, and so that also allows more students to participate. Sometimes there's just one counterexample. In the case of the square, for example, I invite you to think about whether there are any other counterexamples, or whether 4 is the only side length for which the perimeter is the same as the area. And that's also kind of an activity that you can propose to your students. I'm going to leave 9 for you to think about. And maybe let's just do 10. If a rectangle's perimeter is not an integer, then neither is its area. Okay, so as you can see, like the phrasing, the logic of the questions becoming a bit more and more involved. But I claim that if a rectangle's perimeter is not an integer, okay, so again, I mean the magnitude, I mean the number, then the area is also not an integer. What do we think? Is this statement true, or is it false? And if it's false, I need a counterexample. So that means I need a rectangle. So you need to tell me what the length of the sides is, in whatever units you want, inches, centimeters, I don't care, such that the perimeter is not an integer, but the area is an integer. That would be a counterexample. Any suggestions? Maybe it's true. Maybe whenever the perimeter of a rectangle is not an integer, then the area isn't an integer either. But if it's false, then you need to prove me wrong by telling me what are the lengths of the sides of a rectangle. A single example is enough, for which the perimeter is not an integer, but for which the area is an integer. Let's say inches. Let's say everything is in inches. Doesn't really matter. Any suggestions? Okay. Okay, we have a suggestion. So let's see. The proposal is that the length is 6 and the width is 2/3. So let's calculate the perimeter. The perimeter is going to be 6 plus 6 plus 2/3 plus 2/3, which is going to be, let's see, 12 plus 4/3. And that's going to be, it's going to be 13 and 1/3. So that's not an integer. But the area is going to be 6 times 2/3, and that is the same as 4. So that's it. It's a counterexample. So length equals 6, width equals 2/3. Thank you, Lincoln. So so you see now that you have this concrete example, then maybe you can think about what made this example work, and you can think of other potential counterexamples. But it's fun because you're just fishing around to see what works, and you try things and so on and so forth. Okay, so I want to move on to something a bit different, but I just wanted to, go through some sample questions with everyone, so you see just kind of how this game works in practice. Any questions or comments about the activity at this point?
This activity is challenging and exciting for the students as well.
I think so. Anyone else want to share anything? And feel free to, say whatever, speak what's in your mind. Like, we're here to talk together. And okay, so it seems like people like the format. Okay, so here you see I had my own counterexamples that I had come up with, but you came up with many others. Here I also, let's see the question, how would you get students this type of thinking to think more abstract? Well, I think this kind of evolution that we had is good, like starting with statements that are very simple and not mathematical, and for which most children can find counterexamples, like all birds can fly. That's a statement that you can ask any child that can speak, really. So very, very young. And then just very slowly, you can get them to more and more complicated statements and maybe more and more mathematical. And you can come up with, and maybe in a while I'll actually ask you, see if what questions you can come up with. But I think, this is just a sampling of possible questions, but obviously the sky's the limit, and you can come up with all kinds of questions yourselves that might work, and maybe even at some point the students can come up with their own questions. So I think that's a good way to build up. Is counterexample the current diagnostic phrase? I'm not sure what is meant by diagnostic phrase, and I'm also not sure whether they will see this word in the exams. Counterexample it's a technical term in mathematics, like major conjectures in modern mathematical research are disproved when someone finds a counterexample. So it's certainly a technical mathematical term. I would be surprised if the term is used in exams in standardized tests, but maybe someone can disprove me by producing a counterexample if you have any exam where this word has been used, or I don't know if anyone has anything to add. Please.
I think they do see it in SAT and ACT in the college entrance exams. So by the time they're in secondary school, my daughter's been studying for her exams.
Well, there you go. Thank you, Dave. So, okay. So let's do my sample questions. Yeah, so I also wanted to, we've essentially been doing it, but also to this again, just in the materials that I will share later, but this is how a discussion could go, right? So the teacher claims that all animals has 4 legs. And then can anyone think of a counterexample? And maybe one student will say a person, someone will say a spider, someone will say a fish. And then the teacher should ask the students to, or whenever someone makes a suggestion, they can ask them, why is it a counterexample? So you should make sure that not only can a student produce a suitable candidate for a counterexample, but moreover, that they can explain in plain English terms, or whatever the language of your choice, why it is a counterexample. So in this case, why is it a counterexample? Because it has 2 legs. So the person is an animal and it has 2 legs. And then the teacher said, right. So then the teacher can clarify to the rest of the group, because maybe not everyone understood it right away, why it's a counterexample. So the teacher says, right, I said every animal has 4 legs, but a human being is an animal with just 2 legs. So I must have been wrong. And then, for this activity, you can keep on going and refine the question so that the counterexample that was proposed no longer applies, thus inciting students to come up with a new one. So, so in this case, the teacher now says, what about this one? Everything with 4 legs is an animal. And then the student can say, a spider. But actually, that wasn't a counterexample to the question that the teacher asked. The teacher asked, what about this one? Everything with 4 legs is an animal. So maybe the student was confused, or maybe the student was still thinking of the previous question, okay? And the teacher can clarify the situation. Yeah. So in this case, the teacher says, a spider is an animal with 8 legs. So it proves that not every animal has 4 legs, which was the previous question. But I claim that if you have something with 4 legs, it must be an animal. To prove me wrong, you have to give me something with 4 legs that isn't. Okay. So again, making sure that the student understands what is required in order to produce this counterexample. You need to, if the question was everything with 4 legs is an animal, then you have to give me something with 4 legs that isn't an animal. It might, you know, not everyone might immediately understand exactly what is required of them, right? Like they might be a little bit confused, particularly at the beginning, about what a counterexample is. So just repeating in very plain terms exactly what is being asked of the student will be helpful. So you have to give me something with 4 legs that isn't an animal. And then a student maybe then suggests like a table, but maybe they're not very sure of the suggestion, and I think it is a good one. But then if they're not very sure, the teacher can ask the class to help them understand whether it is a counterexample. So the teacher says, who can tell me if a table is a counterexample to my claim? And then maybe some other student has a chance of explaining the logic, and so on and so forth. Okay, so again, this is very broad strokes, but this is a rough example of how this kind of activity could go about, with the understanding that not everything that the students say will actually be a correct counterexample, and so the teacher will have to help them work through the logic and decide which ones were counterexamples and which ones were not. Okay, any questions at this point? Okay. So here are some tips for the classroom. Okay, so like I was saying before, start simple. Don't start straight away with kind of very advanced mathematical problems or even stuff like the.
If I turn my speaker off, you can use your speaker. Okay, I just found it.
Okay, so another tip is to.
I can hear fine.
I think someone might not be muted. We usually get some echo when that happens. So thank you so much. Yeah, so try using silly claims. Okay, for example, you can say the only one who likes cookies is Cookie Monster, and then some student will be, I like cookies, whatever, right? But that's it's good. That is a counterexample to the claim, and it's entirely the point of the game. So starting with silly, fun questions like that can help get them engaged, particularly about the beginning. Another tip, I'm not so sure about this one myself, but anyway, I'm again following these materials, which is to use number talk mechanics. So if something that can happen, I mean, this is something that happens in general, right? Like you ask the classroom a question and you want the classroom to think about it, but then someone immediately blurts out the answer, which is fine, but it robs the rest of the classroom the opportunity to think. Because once someone has already shared the question, then there's not that much for everyone else to do. And so one possible, counterexamples are good because often there can be multiple solutions, multiple examples like we saw. But another way to say it is another way to go about the activity is to have students raise the number of fingers for how many examples they have found. That also allows them, even if they already have thought of a counterexample, to keep thinking of more. And then it can even be a game to see who can come up with the most counterexamples, right? So tip number 4, again, we were thinking of when kids make their own false claims, but sometimes these are the right kind. Yeah, so you can definitely ask students to come up with their own false claims for other students to come up with counterexamples, but of course you might have to do some quality control because not all of the false claims that the students will come up with will work. Okay, so there's a comment in the chat that I want to get to, but I'm just going to finish this list of tips. So yeah, so once you introduce the language of counterexamples, you can look for places to use it in the rest of your math discussions. Because again, there's a lot of claims in mathematics that can be settled by a judicious counterexample. Remember this example of all squares are rectangles, but not all rectangles are squares. So one half of that claim requires some logical deduction, and the other half of it just requires a single counterexample, namely a square where the length and the width are not the same. And so introducing that language into the classroom will be good. Starting with this game is a great way. And you know, Dave mentioned that this does come up in standardized tests later on. So it'll be good to build familiarity with that language. And then finally, number 6 is something that I alluded to, but that you can use counterexamples to motivate a normal math question. Instead of saying, draw a triangle with the same area as this square, you can say, I claim there is no triangle with the same area as this square. And so if the students are familiar with this dynamic, this will set them to work to trying to disprove the claim right away. And like I've mentioned a couple times, you have the added excitement of proving the teacher wrong. So I invite you to think of when you're going to share activities, when and where you can use the language of counterexamples to spice up the conversation. Okay, so there was a comment that the Freyer model has a non-example section. So I don't know what the Freyer model is, but maybe someone can tell me or share something more about that. Vanessa, I don't know if you want to do it yourself or someone else wants to chip in, but please feel free.
Yes. So the whole idea of using the Freyer model is just to get them to talk about the concept that is being taught. So they want the students to know the definition of the vocabulary word, and then they have an example that we would have to show them, and then I was thinking the non-example could be used in that sense in that area. So we were just going over properties of multiplication, and I noticed that they were struggling with associative and distributive property because of the parentheses. So I was just thinking in that sense, like just showing them something that is not, let's say, for example, the associative property. So they would have to, I guess, from there, so it would be just framing it would probably be where I would have a hard time putting in a sentence, but because I teach 3rd grade, so we introduce those concepts then. I guess that was what I was thinking.
Great, thanks for sharing. Okay, anyone else want to share any thoughts or suggestions or anything really? Okay, so I think I still have a few minutes. So one possible tool for counterexamples that you can use is this pattern blocks that was linked in this resource. So let me show you what it is. I'm gonna put the website in the chat, and I invite you to open it in a browser. But basically this, so I believe there are physical models, and Dave can talk more about this if he wants to, but there's this online version where you can build shapes using other shapes. You can rotate them and put them in whichever way. And we're going to go over some activities in the counterexample theme that you can go over, then you can work on with this tool. But there's other activities too that I also link below in the document. Dave, do you want to say anything about the pattern shapes?
I was just taking a second to unmute. So yeah, in fact, we had a teacher request pattern blocks for their students. So I mailed them the classic pattern blocks recently. In fact, Dan, oh, I'm losing his last name for a second. The Math for Love, Dan. I designed a new set of pattern blocks called 21st Century Pattern Blocks. And so I sent this teacher sets of both the classic pattern blocks plus the 21st Century Pattern Blocks. And I think we'll do a session on mathematical uses of pattern blocks because I think there's a full session here. This is something we can provide to teachers who wish to do it. So I'm putting on the website now a handout on the Freyer model, which is a description of a way to capture definitions and help students learn vocabulary. And I'll put your links up on it as well.
Cool. Thanks. So concretely for this activity, you can ask all kinds of questions, but you can phrase them as challenges. So you can ask, it's impossible to make a hexagon with pattern blocks that isn't yellow. And then, okay, so let's have a look at that one. It's impossible. I'm going to write it here in the chat. And so I invite you, if you have the link, to open the browser and play with this and see if you can make a hexagon with pattern blocks that isn't yellow. And if you figure it out, you can tell me how you did it. Let's agree it's a regular hexagon. So of course I can make a regular hexagon like this with just a single yellow pattern block, but can I make a hexagon that is a regular hexagon with pattern blocks that isn't yellow? Any suggestions? Okay, so I have already one suggestion, which is to use two reds, two trapezoids. Great. So that's one. And then I also have another suggestion, which is to use 6 triangles. And then that's going to be green. Okay, and you can think of other ways to do it, but this is, for example, an activity that you can challenge your kids to do, and if you have the blocks, then you can do it with the actual blocks. If you have a computer, then you can do it with a computer. But there's a whole number of activities that you can do. The main exploration described here are the challenges 4 and 5, which is it possible to build a hexagon with any number of blocks? Okay, so this is kind of fun. So, for example, so before you do that, challenge 3 was making hexagons with 1, 2, and 3 blocks. So let's see if you can make a hexagon with 4 blocks. So let me say it is impossible to make a hexagon with 4 blocks. Can someone prove me wrong? If it's wrong, then there must be a way to make a hexagon with 4 blocks. Okay, so one suggestion is to use 2 blue and 2 green. Great. Okay, what about it is impossible? Okay, well you get the idea. So to make a hexagon, you can do 1, 2, 3, 4, 5, 6, 7 blocks. You can, I'm not saying you should do all of them now, but you can ramp it up. You can start with just 1 block and then you just get a hexagon. Then you do 2, as we can see, we can do it with 2 reds. You can then go to 3, 4, 5, 6, 7. And once you've done that, so 7 is quite interesting. And then the follow-up would be, it is, so then you can ask, you know, it is impossible to build a hexagon with 100 blocks. And then how would you actually disprove this? Well, I mean, you could really build one with 100 blocks. Sounds like a lot of work. But I think if you start playing with the blocks and you do 1, 2, 3, 4, 5, 6, 7, you keep on going, maybe up to 20 blocks, then maybe some patterns will start to become apparent. And then maybe you don't even have to build it explicitly. You can just say how you would build it. So anyway, that's a fun little activity. There's more pattern block challenges on this website that I also have linked. So this is the website. The challenge that it gives you is to fill in certain shapes with blocks. So this seems like another fun activity that you could do with the student. So I just linked that there in the sheet for you to look at if you're interested. But it all sounds like fun stuff. Okay, I have some examples here that I will go through quickly so I don't rob you of the pleasure. But I just wanted to touch on here, you know, among friends, a little bit of the logic behind all of these ideas that we've been talking about. So, you know, one of the common statements that we have been examining is a statement of the form, all X satisfy property P. Or if I want to be even more succinct, I could write this as all X satisfy P. Okay, where so P is some property, and X is a class of objects. For example, you know, so it could be all flowers are red. So X would be flowers, and P is being red, and that's a statement that is being examined. That statement is logically equivalent to no X satisfies the property not P. Okay, I'm gonna put not P in brackets, and by not P I mean the opposite of property P. So the statement all flowers are red is the same as no flower is not red. Okay, I'm just gonna write that in the chat. that all flowers are red is the same as no flower is not red. These are equivalent statements logically. And so in order to disprove the statements that all X satisfy P, it's the same as to prove that some X does not satisfy P. And that's what you're doing when you're finding a counterexample. So to disprove the statement, all flowers are red, it is the same as to prove the statement, sunflower is not red. And to prove the statement that sunflower is not red, it suffices to give a single example of a flower that is not red. Okay, and so that's kind of what's going on. And in general, the negation of the statement that all X satisfy the property P is that some X does not satisfy property P, or there exists some X for which property P does not hold. And what I want to highlight for us, the teachers, is what is happening when we negate the statement. All is replaced by some, and property P is replaced by not property P. Okay, so you swap. So what is the effect of negating a logical statement in mathematics? This is true in all generality. The effect of negating a mathematical statement is that all is swapped for some. Let's say, no, yeah. And some property P is swapped for not property P. So I don't want to dwell in this because it will quickly become a bit too abstract. But this is all in the material, so I invite you I invite you to reflect on this fact of logic, which is that when you negate a logical statement, all gets swapped for some, or there exists some, and a property gets swapped for not that property. And that's just some of the logic underlying all of this discussion. I don't really have time to dwell on this, but we have been, before there was a question, a claim that I was proposing that every number is a rational number, and some counterexamples were suggested, like square root of 10. But then I asked, how do you know that 10 is not a rational number? And here I just include, for your amusement, an old argument, 2,500 years old at least, of why the square root of 2 is not rational, but any other square root will do, really. So if you want to have fun with that old argument, it's a very beautiful and subtle argument, but I won't go into it right now because it's kind of besides the point, and I just leave it there for your enjoyment.